Alright, let's go. Number 6. The entropy that should not fit. In 1972, Jacob Bekenstein, then a graduate student at Princeton working under John Wheeler, proposed something that unsettled his own advisor. Bekenstein was studying black holes and asked a simple question: how much information can a black hole hold? Working from the laws of thermodynamics, he derived a formula suggesting that a black hole's entropy, its hidden information content, was proportional not to its volume, but to the area of its event horizon. Classical physics expected the opposite. Every system anyone had ever measured stored information in proportion to volume. A box twice as large should hold roughly twice as much information. The Bekenstein bound, later refined alongside Stephen Hawking's 1974 work on black hole radiation, broke that assumption directly. It stated that the maximum entropy of any region scales with the area of its boundary, not the three-dimensional space inside it. The violation deepened when Hawking calculated black hole temperature and entropy explicitly, arriving at the Bekenstein-Hawking entropy formula: S equals the horizon area divided by 4 times the Planck length squared. A black hole the mass of the Sun has an entropy so large it dwarfs the entropy of the same mass spread out as ordinary matter, and that entropy lives entirely on a two-dimensional surface. Physicists tried to explain this away as a mathematical curiosity specific to black holes. It wasn't. The bound applied, in principle, to any region of space: a room, a planet, a galaxy. If true, the three-dimensional volume you are sitting in right now may contain less actual information than the two-dimensional surface enclosing it. Today, the Bekenstein bound is considered one of the few rigorously derived constraints connecting gravity, thermodynamics, and information theory, and it has never been experimentally violated. Leonard Susskind at Stanford and Gerard Hooft at Utrecht University would later build directly on this result, but even now, no complete derivation exists explaining why nature would organize information this way at a fundamental level. The debate over what physically stores that boundary information remains unresolved. Volume was never the container. The surface was. Number 5. The universe as a flat projection. In 1993, Gerard Hooft at Utrecht University published a paper arguing that Bekenstein's entropy bound was not a black hole oddity, it was a clue about the structure of reality itself. Leonard Susskind at Stanford expanded the idea in 1995 into what is now called the holographic principle. The proposal: everything that happens inside a three-dimensional volume of space can be fully described by information encoded on its two-dimensional boundary, the way a hologram encodes a 3D image on a flat piece of film. The established expectation in physics, going back to Newton, was that space has 3 independent dimensions, and that physical information genuinely lives throughout that volume. Locality was sacred. What happens here should not depend on encoded data somewhere else entirely. The holographic principle inverted that. It suggested the 3 dimensions we experience as fundamental might be redundant and emergent illusion generated by information stored on a distant boundary, possibly the cosmological horizon itself. Hooft and Susskind weren't proposing a metaphor. They were proposing that the universe has, at most, a finite and computable amount of information, bounded by area, and that our perception of depth and volume could be a derived effect rather than a basic feature of nature. If correct, every particle's position, every interaction, every memory you've ever formed would be redundant data fully specified by a flatter, lower-dimensional reality we cannot directly observe. Susskind has stated the principle is likely a deep truth about quantum gravity, while others, including some loop quantum gravity researchers, argue it may be specific to certain spacetimes rather than universal. No experiment has confirmed or falsified holography directly in the years since Hooft's original paper. We may be the shadow, not the object casting it. Number 4. The noise that shouldn't exist. In 2009, Craig Hogan, then director of the Fermilab Center for Particle Astrophysics, proposed that if the holographic principle were physically real and not just mathematically convenient, it should leave a detectable signature, a fundamental graininess in spacetime itself, a kind of irreducible jitter at extremely small scales, later nicknamed holographic noise. Standard quantum field theory predicts that spacetime, while quantized at the Planck scale of roughly 10^35 meters, should otherwise behave smoothly and continuously at any scale instruments could realistically probe. No detector should pick up correlated, broadband noise from the geometry of space itself. That noise should be far too small to measure with existing technology. Hogan argued the opposite was possible. If information is truly stored on a 2D holographic boundary, the pixels encoding 3D space might be large enough, around 10-16 meters, vastly larger than the Planck length, to produce a faint but measurable jitter. And he predicted this jitter should appear as correlated noise in interferometers, like the GEO 600 gravitational wave detector in Germany. In 2011, GEO 600 researchers, led by Karsten Dansman at the Albert Einstein Institute, did report an unexplained noise excess in their data at frequencies above 300 Hz, noise they had struggled for years to identify a conventional source for. Hogan suggested it matched his prediction. Most physicists, including members of the LIGO collaboration, argued the noise was far more likely instrumental, a calibration artifact, not new physics. And Hogan's own holometer experiment at Fermilab, completed in 2015, found no holographic noise at the predicted level. The GEO 600 anomaly was never fully explained even after Hogan's prediction was set aside. Researchers attribute it to instrumental noise, but the original source was never definitively pinned down. Some scientists, including Hogan himself, maintain the question deserves a more sensitive instrument than what existed. The static was never explained. It was simply stopped being asked about. Number 3. The theory that made the boundary the whole story. In 1997, Juan Maldacena, then at Harvard University, published a paper that would become one of the most cited results in theoretical physics, the ADS-CFT correspondence. Maldacena showed that a theory of gravity operating inside a 5-dimensional curved space called anti-de Sitter space is mathematically equivalent to a conformal field theory, a theory with no gravity at all, living on that space's 4-dimensional boundary. Before this, gravity and quantum field theory were treated as fundamentally separate languages, one geometric, one particle-based, with no exact mathematical bridge between them. String theorists expected dualities to exist in principle, but no one had constructed a precise, calculable example linking a gravitational theory in a volume to a non-gravitational theory on its boundary. Maldacena's correspondence did exactly that, and it is held up under 2 decades of mathematical scrutiny. Calculations that are intractable inside the gravitational bulk become solvable on the boundary, and vice versa. Physicists routinely use ADS/CFT to study strongly coupled quantum systems, including aspects of nuclear matter and condensed matter physics, by translating problems into the dual boundary theory. The catch, acknowledged openly by Maldacena and by Edward Witten at the Institute for Advanced Study, who extended the framework that same year, is that the correspondence is rigorously proven only for anti-de Sitter space, a universe with negative spacetime curvature. Our universe is not anti-de Sitter. It is de Sitter, with positive curvature and accelerating expansion, and no one has constructed an equally rigorous holographic dual for it. ADS-CFT remains, by most accounts, the strongest formal evidence that holography is mathematically real. Whether it describes the actual universe we inhabit, rather than a close mathematical cousin of it, remains an open question that has resisted 30 years of effort. We proved holography works perfectly. We proved it for a universe that isn't ours. Number 2. The wormhole hiding inside every entangled pair. In 2013, Juan Maldacena and Leonard Susskind published a short paper proposing something that startled even researchers familiar with their earlier work, that quantum entanglement and wormholes, Einstein-Rosen bridges connecting distant points in spacetime, might be the same phenomenon described in 2 different languages. They called it ER/EPR, fusing Einstein and Rosen's 1935 wormhole paper with Einstein, Podolsky, and Rosen's 1935 entanglement paper, published in the same year by the same physicist for unrelated reasons. Quantum mechanics had always treated entanglement as a purely informational correlation, with no geometric meaning 2 particles could be correlated regardless of distance. But nothing was supposed to physically connect them through space. Spacetime geometry and quantum information were considered separate ingredients of physics, one describing shape, the other describing correlation. Maldacena and Susskind argued that any pair of maximally entangled black holes is connected by a wormhole through the bulk geometry, and, more radically, that this might generalize, that entanglement between any two quantum systems could correspond to a tiny, non-traversable wormhole linking them, too small and too unstable to send anything through, but geometrically real within the holographic framework. If correct, space-time itself, its connectivity, its very existence as a continuous fabric might be built out of quantum entanglement, stitched together one correlated pair at a time. Mark van Ramsdonk, at the University of British Columbia, independently argued in 2010 that disentangling enough of a quantum system causes its dual spacetime to literally tear apart. The conjecture remains unproven in general and is considered speculative even by its authors, though it has reshaped how a significant portion of the quantum gravity community thinks about spacetime's origin. Susskind has stated plainly that he believes geometry emerges from entanglement. Others, including some loop quantum gravity researchers, remain unconvinced that the analogy survives outside idealized black hole cases. Two particles, never touched again, still bridged by a tunnel through nothing. The fabric of space may be sewn from connections you cannot see and were never meant to perceive. Number 1. The universe that holography cannot describe. Every entry so far has built toward a single, quietly devastating fact. The strongest mathematical evidence for the holographic principle exists almost entirely for anti-de Sitter universes, and we do not live in one.